All right. Well, thanks for joining everyone, and welcome to the third and at this point last tutorial in the series of tutorials for how to access and how to use this open access solar data that we came to be able to publicize with the Solar Data Bounty Prize using open source tools that have been developed and maintained by the national labs. So if we can go to the next page, please.
Apologies.
All right. So probably you have heard this from me or from others during this tutorial again, but I'll just go very briefly over it. I mean, the whole point here is to get high quality data in order to improve models for the performance of PV system. And those models are important for two reasons. One, they're very useful, critical actually, in the project development phase and especially the valuation phase of a PV project. And they're also very useful in essentially making it easier for us to understand the performance of the power plants and therefore optimize any maintenance that's required. In the grand scheme of things, better system performance means always lower cost of solar electricity. So that was the prize goal that we launched last year, right, to support industrial and academic research, so that every stakeholder can develop, improve, evaluate, and validate models of systems from real-world systems that come from diverse set of environments. Next slide, please. So this is the structure of the three tutorials so far, right? So the first tutorial last week, you guys learned how to access the datasets from the prize. A couple days ago, you saw how to analyze the data and understand the system performance that is visible by that analysis. And today, my colleagues Matt and Kevin will share with you some aspects of modeling systems using the open source tools I mentioned, SAM and PVLib, using data from the prize, like one of the winning systems from the prize. Without further ado, I'll give it over to Matt. Thanks, everyone.
Thanks, Tassos. So yeah, today, like Tassos mentioned, we'll be going over demos for open source PV modeling tools, PySAM and PVLib. PySAM is the Python wrapper of the SAM System Advisor model source code, and PVLib is a toolbox of PV functions for full calculations of PV performance models. As Tassos mentioned, I'm Matt Perliman. I'm a researcher and core developer on the System Advisor model and PVWatts. SAM, as it's more commonly known, is free software that enables detailed performance and financial analysis for renewable energy systems. So full techno-economic analysis of PV and also other different types of renewable energy systems. This is primarily accessed through the desktop tool and through our PVWatts web tool and API. But there's also a robust software development kit that includes our PySAM wrapper of the SAM source code. And that's what we'll be going over today for using PySAM for some unique data features to use the prize data and some of your analysis for comparison and for advanced analysis features. And all the SAM source code is open source and is extensively documented for both the PySAM documentation and the SAM documentation. The way SAM is structured, we take in weather data, whether it be from measured from the site or from the NSRDB or other data source satellite data sources, system specifications that the user defines, and system losses to get performance metrics that are then combined with cost of the system, incentives such as the ITC, different financing considerations for both front of the meter and behind the meter perspectives, and compensations such as agreed upon PPA prices or other revenue sources to get financial metrics from your system, such as your net present value, levelized cost of energy, estimated payback period, and other discounted annual cash flows as well. PySAM is again, the Python wrapper of the SAM source code. You can generate PySAM code to use in your Python analysis through our software development kit tool that has a code generator. I have links here for when the slides are shared to access the PyPy. It's just pip install nrel PySAM. And this week we've actually updated to version 5.1.0 to coincide with the release of the SAM desktop tool patch 1 release. So be sure to check that out. And I have links to our read the docs and our GitHub repo for PySAM as well. And with that, I'll hand it off to Kevin to introduce PVlib.
Thanks, Matt. So PVlib is an open source software package also for modeling the performance of PV systems, but it does take a somewhat different approach to SAM. It looks like this slide isn't rendering exactly correctly, so I'll just talk through it. The idea here is not so much that it's focused on end-to-end system performance models where you give it a weather data set and a system configuration, and you get a energy delivered to the grid as the output. You can do that, but we call it a toolbox because it's really more of a collection of individual modeling pieces that you can combine and use to do many different things. And so it's quite a flexible tool. It also has an emphasis on transparency and open development, meaning that all of its code is open source and easily dug into. It's all written in the Python programming language. And so it's really easy to go into the source code and read exactly what's happening for any given model. It also provides many alternatives for each modeling step. And there might be, for example, I don't know, a half a dozen different transposition models, for example, in PVlib Python. And one other thing I want to highlight here is its data I/O capabilities. This is something that we've built out quite a lot over the last couple of years, providing functionality for fetching data, weather data from many different online providers, as well as providing functions to read local data files on your own computer in many different formats. Let's go to the next slide. Oh, sorry, I clicked through. So just to give you a sense of what I was talking about with many different alternatives for different models here, here's just a selection of different sub-packages within PVlib organized by modeling topic, and starting with solar position and going on from there. And again, we couldn't list all of them. This is a small selection of them, but I mean, just looking at pvlib.temperature in the center bottom, these are all different thermal models within PVlib Python that take in things like irradiance and ambient temperature and produce an estimate of module temperature. And with all of these different options, these are all backed by peer-reviewed journal articles or other references in the scientific literature. That's true for all of PVlib's models implementations. Next slide. Here's just a quick overview of the I/O tools package I mentioned. You can think of it as being split into two main parts. The first part is looking at ground station measurement locations. And so these are real instruments located at ideally research grade institutions around the world, measuring oftentimes solar resource, so primarily irradiance measurements, but they also make auxiliary measurements relevant to PV modeling. So PVlib has many functions for fetching and importing data sets from these ground station networks and making them into a form that's really convenient to use for PV modeling purposes. It also has many functions for fetching data from satellite and reanalysis-based data sets. And so if the system you're interested in modeling doesn't happen to be right next to one of these high-quality ground station locations, then you can use these estimated weather data sets instead. And as you can see, we have quite good geographic coverage with these data sets. Next slide. So similar to PySAM, PVlib Python is on the Python package index. You can pip install it. It's also available in the Conda Forge channel if you prefer to use Anaconda. And here are the links for documentation development and our online Google group forum, which I encourage you to sign up for if you aren't already in there. I think now, yeah, we're going to get into the demos. So back to you, Matt.
Yep, I will start our PySAM demonstration here. Okay, so today I'll be going through demonstration of some of the ways to use PySam, in particular ways to use PySam in ways that leverage the data from the data prize, DOE data prize. I'll go over here at the top, we have a Venn diagram of some of the stuff we just mentioned about the strengths of PVLib and PySam. And we'll come back to this diagram at the end for maybe some guidance, high-level guidance on which tool makes the most sense for your analysis, or maybe both. So both great tools. So today I'll be going over setting up the PySam case. So I will be importing the relevant PySam modules, so our detailed performance PV model and how to use that, and some examples of financial models. Different ways to load in weather data to use in your analysis. I'll go over setting up the PV system design, which is best done through starting, for new PySam users, is best done by starting in the SAM user interface, the desktop tool, and then exporting code to use in your PySam analysis. I'll go over running the model both on an annual basis for a full year of NSRDB data and for running non-annual simulations where you can look at segments of days or months or single time steps in your simulations. I'll go over comparisons of some modeled SAM results to measured data from the data prize, and then I'll go over a couple of extra model features to use some additional data series from the prize, such as tracker rotation angles and measured module temperature. So to begin by setting up PySam, you can just import PySam the way you would any other Python package. I imported it as PySam, and then I imported our PVSAM v1 module as PV. This is our detailed PV performance model. In addition, there's the PV Watts module, which runs the same underlying CEC single diode module performance model, but has just a lot less user inputs and a little bit simpler system design and sizing for the system. And that the latest version of that is PV Watts V8 is the name of the module. Also, I'm incorporating the fixed charge rate LCOE calculator for a quick example on how to pair your SAM analysis with financial results. We do have more detailed financial models available, but today I'll focus on the LCOE calculator. I'm using pandas for a lot of the data processing and matplotlib for some simple plotting. So the first thing with any PV performance modeling setup is the weather data. For PySam, you have two options here. You can use a weather file data formatted either with measured data or with data downloaded from sources such as the NSRDB that fits within one of SAM's formats. SAM takes in what gets downloaded from the NSRDB. It also accepts TMY formats and other common weather file formats. I'll show in a second how you can download those NSRDB files directly from the desktop tool easily. And there's also some fetch tools within PySam ancillary functions to pull from the NREL developer network and the NSRDB data as well. The second option, which is useful for non-annual simulations, is to store your solar resource data in a dictionary using these different tags for the different elements of your model. The key ones here, such as the some combination of DNI, DN, diffuse DF, or GHI, GH for weather data, or POA as for calculating from plane of array irradiance, and wind speed and ambient temperature or dry bulb temperature, T-dry. I'm loading in data from system 9068 for this example. That's the SRCO system in the database. Doing this to look at some single axis tracking applications, and the system is a single axis tracker with so I'm loading in irradiance environment data and also going to be looking at performance data and tracker angle data as well over the course of this example. And loading in some of that data from pandas here. I have thermocouple measurements for module temperature, weather station ambient temperature, and other data streams as well. And just pulling in a single year of data for this analysis to start with the annual simulation. flowing into, once you know your weather and you have your data to compare against and use for weather data, is setting up how to design your system. So for new PySAM users, we do recommend starting in the user interface, which I will bring up here as an example. So this is our SAM desktop tool. You can see when you load in a case, you have a variety of tabs here. You have photovoltaic modules for the detailed PV model, and then a variety of financial perspectives. I'll just load in another one here. But for system 9068, I started by just loading in here. Started by downloading data from the NSRDB from the same site as the system by going to the solar resource page, location and resource, and you have the ability, once you're signed into SAM and registered, you can search by a lat long or a city state address or a street address to find data for the closest NSRDB data set for that site. And there's also some advanced download features as well. You can select a specific module with parameters already defined for the CEC performance model from the CEC module database that gets updated regularly, or you can make a module with user entered specs for custom modules. Similarly, for an inverter, there's libraries to choose from, or you can make a data sheet for your own inverter for the system. System design, this is where you can set the size of your system and how many modules in a string, how many strings. You can set the tracking, single axis tracking for your system with the tilt of the tracker or the azimuth that the system is facing, the GCR and the tracker rotation limit. SAM does enable calculating for slope-aware backtracking for a constant slope, and SAM does model up to 4 subarrays with different configurations for each subarray. You can turn on shading models, self-shading, row-to-row shading models for your system. So because this is a thin film system, I turned on our thin film shading model. I use default losses for the system just for the sake of this example. And once I finish setting up the system in a way that makes sense and what I want to use for my analysis, I can go to this arrow for the case here, and I can generate code. And you can see our code generator here has the ability to generate code for a variety of different languages. And at the bottom here is the key one for today, our PySAM JSON. This will generate, and in the folder you select, it'll generate JSON files with all the relevant inputs for your system, which is a lot of inputs for this detailed PV performance model. And we'll carry over your weather file and other information so that you can start in PySAM modeling your system. So I've already done that for this case. So I will continue back to Python. And here I'm just showing an image of that same process, generating code and making PySAM JSON. Next, this is a key cell here, because we're generating a new instance of that PV model that we pulled from PVSAM v1 called PV model. And then we are opening that JSON, which is named after the name of the case and then the name of the module, PVSAM v1. And we're going to load from that JSON and then assign the values of each of the named variables in that JSON to that case. So then now we have a case fully loaded with our system design and all the relevant input parameters to go off of. Next, I can show again an example of the solar resource data, where if I wanted to use data from the data sets, the prize data sets, I can load in tuples of that data. So for this solar resource data, I can load in all the relevant information, time series, POA, wind speed, and dry bulb temperature. But for starters, in the solar resource group, so the PySAM modules, such as this PV model that we made from PVSAM v1, are organized into different input groups. This was automatically assigned for everything in the JSON in this process here, but for like assigning the weather file, which is in the solar resource file, that's part of the solar resource group. I can assign it with this assign function here, and then give it the name of the CSV with our NSRDB weather data, and run the analysis that way, starting from file. So the PV model will always look for the solar resource file first, and then if that is not assigned, then we'll look for this solar resource data, which I will assign in our next example. Running the simulation to get performance outputs is as simple as the pvmodel.execute to run the module. 0 and then a 1 if it's execute with a 1, that's for verbose outputs. You can access all the outputs from that simulation in the outputs tab, and then any change to inputs you'd have to execute again to see the effect of that change in input on the outputs. So I execute, I export all the outputs into a dictionary and then load them into a pandas data frame for plotting. And I get a 5-minute data series of power output over the year of that weather file in question. And then, so this could be useful in comparing to measured performance data. So I can use the data from the prize to compare against our results, and can look at first the entire year, and then I'll get into how to focus on specific subsets if you want to model less than a year of data. So I'm reading in more data from our 9068 system, reading in power data. I am setting up the index to be based on the time series within the data. I am pulling for a specific year. And looking at the combined output, the system has 2 inverters, and I'm looking at the combined output of both, so I'm adding those together. And then I am plotting the actual power against the predicted power over the full year to get a quick analysis of the results. Some gaps in the measured data, but you can see, looking at the simulated results to the actual measured results, some differences here. I didn't account for any kind of like snow modeling or anything in my power predictions. And the NSRDB weather data is not an exact match with the ground measured data from the site, which I will use in the future analysis. Next, I'll show how to connect, let's say, the LCOE financial model. As I mentioned, Sam has many detailed financial models to show discounted cash flows for project revenue, operating costs, incentives, and all other financial aspects. These are modeled both from the meter perspective, such as a single owner of a utility scale system perspective, or a residential or commercial perspective, commercial building owner, residential homeowner perspective for behind the meter systems that are getting value from lowered electricity bills. So I do the same thing to load in our LCOE model. I load in the LCOE module that I made earlier and start a new instance of that. This only has one group, the simple LCOE group. And I am taking the annual energy component from the outputs of the PV case I ran previously. So linking those there. I'm putting in fake numbers for just a quick example of the LCOE. These are not indicative of anything for the actual system. So capital cost number in dollars, fixed charge rate as a percentage or a decimal in this case, annual operating cost in dollars, and then a variable operating cost number in dollars per kilowatt hour per year. Executing that, and then the only output for this simple LCOE calculator is the LCOE, and looking at that in dollars per kilowatt hour. Next, moving on to focus on the non-annual simulations. This is one of the great values of PySam, because this type of only running a subset of a year or a single time step, single day of analysis, single month is only something you can do in the software development kit, so outside of the desktop tool. You can use these features to monitor measured versus modeled results based on the incoming data streams, or look at data over the multiple years of data in the prize data sets. You can focus on segments of the year and individual days, as I mentioned. It's easier to do parametrics, faster to do parametric sweeps sometimes using these subsets of the non-annual simulations, iterate over ranges of inputs, and look at the impact on results. And I'll go over how to use that solar resource data instead of solar resource file. So to start this, starting over with my PV model, just making it a new instance to this time focus on only one of the inverters rather than both of the inverters in that 9068 Colorado system. Same loading in that JSON. I had that case also in that same desktop, SAM desktop tool file, which are saved as .sam files. So loading in that and loading in the values to the model in the same way. To use the solar resource data, I am unassigning any value for the solar resource file, so that there's no file to read from for weather data, and unassigning any other values that aren't relevant to this case as well. I am picking a specific day from the prize data, looking at the weather data, particularly the POA, plane of array irradiance data, the wind speed data, and the dry bulb temperature. So I am picking a particular day out of the ambient weather data and the weather data for the prize. I am setting this dictionary by setting the time zone of the system, the elevation, if that's known, the latitude, longitude, and then the year, month, day, hour, minute by using the index that I set for the prize data, did that using pandas, and I'm assigning all these as tuples just for the data processing. For the POA, I'm reading this particular pyranometer from the data. I am picking this particular series for the wind sensor and the weather station ambient temperature as well. And then I am assigning the solar resource data, as I did the same for solar resource file, to the solar resource group. And importantly, for all this to work, I am changing this input variable arrayed mode to 4. This coincides with, if I go back to the desktop tool quickly, all of the input ranges and valid inputs for the variables are available in the Python documentation, but it can also be helpful to visit this, to reference the desktop tool, because, sorry, the bandwidth is making things go a little slow, but coincides with this weather file, how to process the irradiance data option in the desktop tool. So SAM can model based on any combination of DNI, DHI, and GHI, 2 out of the 3, or, so this is 0, 1, 2, 3, 4. 3 is assuming that you have plane of array irradiance measured from a reference cell, which is assuming that the angle of incidence effects are already taken out from the measurements from the reference cell. And 4, which is what we're using in this case, because the data series is from a pyranometer, accounts for those angle of incidence effects that are not included in the pyranometer measurement. So it can be helpful to reference the desktop tool when using PySAM as well. So I set that arrayed mode correctly. I run the analysis, and then I can, in the same way, I'd be able to look at outputs and results. And this type of non-annual simulation can be useful, especially for some specific analysis features that are available right now only in PySAM. The first one that I'll talk about is using modeling for custom tracker rotation angles. So you can see here, I'm starting this process by loading in some data from the tracker rotation angle data for this 9068 system and setting the time index for that as well. So right now in the SAM PV model, the single axis tracking for the SAM is based on the sun position. So the trackers are moving to reduce the angle, to minimize the angle of incidence between the modules and the sun. This does account for backtracking, and it does account for slope-aware backtracking, as I mentioned, thanks to contributions and research from Kevin, who will talk next. But SAM is open source, so we do welcome contributions like that if anybody ever has peer-reviewed models or bug reports or anything like that. So SAM has that sun following tracker algorithm, but there isn't the custom models for like diffuse radiance optimization, or there aren't any controls right now for making the tracker get stuck at certain times or things like that. So what we do have in PySAM at the moment is the option to put in a custom time series of tracker rotation angles rather than model rotation angles to account for these different tracker uses in the field and model that in the performance calculations. So as I mentioned, this is currently only in PySAM. We've already gotten some very helpful comments about interest in these types of features for the desktop tools. So we're definitely looking at how we can incorporate that in the future across all of the SAM and PySAM features. So I'm pulling in tracker data for a day where the tracker didn't move for the whole day and power was being produced. Started by executing. So the input for that is this subarray 1, use custom rotation angles, use custom rot angles. Subarray 1, again, this refers to in the SAM tool, we can model up to 4 subarrays, and each of those has their own system design parameters. So if you were to model 2 subarrays and you wanted to do different rotation angles for each, you would do the same thing, subarray 1, subarray 2. So this is a prefix to a lot of these input variables. By default, SAM always models subarray 1, and then 2 through 4 can be enabled depending on the users how they set them, and that will be carried over from that PySAM JSON as well if it's built in the user interface. So I set the use custom rot angles to 1 to turn it on, 0 for off, 1 for on. I then set that custom rotation angle array to the data that I took from the 9068 data. I execute the system and look at the results, compare it to the measured system data. So looking at the power output first for the measured system data and the model for the tracker with the system not moving. And then just to give a better idea of what's actually happening, looking at how SAM would normally calculate the sun position angles, so changing throughout the day, and then this custom array of rotation angles. SAM, just for the case when there's no power being output, it sets the tracker rotation at 0, but then it follows that input tracker rotation data for the relevant times throughout the day. And we can do a similar thing for module temperatures. So Kevin will talk about in a second. There's a lot of, SAM has a couple of different module temperature models and cell temperature models. Maybe those models you want to compare against measured temperature with everything else in the model being the same, or you want to do some other kind of analysis. So in the same way you do custom rotation angles, you can do custom cell temperatures, where you turn on the feature by setting this to 1, and then pull in data from the measured thermocouples on the modules to set the array of temperatures, module temperature of that day, and then calculate to look at the temperatures for the system versus model temperatures and how that affects the results. So that's just kind of a overview of some different features that you can use PySAM for, different analysis features. I think the non-annual simulation is a key one for a lot of monitoring things, kind of a sanity check of measured versus modeled, how things are looking. And you can do that on a time step by time step basis. You can set that up as part of your workflows. So that's a look into PySAM. And I think now I will pass it off to Kevin to give his analysis with using PVLib. And I will stop sharing now.
Thanks, Matt. Okay, hopefully this is coming through. Like Matt just said, I'm going to be talking about using PVLib Python with these data sets. It's going to be, again, in the form of a notebook. At the top here, why don't we just do some quick things, and then we'll describe what we're going to be doing today. So importing PVLib is step one. I'm also importing some other packages just to help out with the rest of the work I'm doing in this notebook, one for plotting, pandas for data import and general data manipulation, and JSON for reading one of the files from the data prize. So I'm just going to go through. It's always a good idea to check what the versions of the key packages you're using are, in case, if you install it today and then in 6 months you want to use some fancy new function that you saw in our online documentation or you saw one of your coworkers using, but it doesn't exist in your Python installation because yours is old and it was a new addition since you installed PVLib. This is how you can check it. So today I'm using version 0.10.3. This notebook is going to be using system 9068, which is the same one that Matt was just looking at with Sam. This is a system in Colorado. As he said, it's a tracking system with cadmium telluride modules. Here's what it looks like. So it's a sort of small utility scale system. And I'm just going to grab a couple of key parameters here for later use in the notebook. Just the coordinates, we're going to use that for solar position calculations later. And we're also going to read in some measured data from the system. And these are the same data files that were described in part 1 of this webinar series. So there's going to be 2 use cases here today. The first one is based on from the perspective of a system modeler. So somebody that is doing a whole lot of modeling, is evaluating different modeling alternatives to try to get to the best overall model for a particular system. And they might view a data set from, for example, the data prize as an opportunity to benchmark different models against each other and evaluate their accuracy. So that's what we're going to do in this first use case, is primarily be thinking about models and then bring the data in as a validation means. So just as an example of this, I'm going to be using thermal models for this, models that predict the PV module temperature based on other weather inputs. And so before we do anything else, let's just see what data is available to us in this data set. It's quite a lot. We see that the first one here, so this is a list of columns in the CSV file. The first one is an ambient temperature. That's great. We can use that. The next 4 are thermocouples that look like they're mounted on the backs of the PV modules. So this is what we can use to validate our model predictions, because that's the measured module temperature. There's some wind speed statistics, and then many temperature fields related to inverters. These are probably internal inverter measurements, and so not of interest to us in this context. And there's many of them. There's also some other inverter fields. So we're just going to pay attention to these ones right at the top of the ambient temperature and then the measured back module temperature, as well as the wind speed. I'm going to go ahead and collapse this so it's not taking up so much space. So those are the fields that are available. Why don't we see what the actual data looks like? So what I'm doing here is getting a list of the columns that I want to plot, which is the ambient temperature and then the 4 back of module temperatures. And just choosing an example day. So this is August 17th. I just chose that basically randomly. And if we plot it, we can see blue here is the ambient temperature, and the other 4 lines are the measured module temperatures. And so this seems pretty reasonable to me. There's no obvious unit issues. They're not secretly in Fahrenheit or anything like that. It seems like this is a fairly variable day, and that's why the PV module temperature is going up and down like this. Probably that's due to changing cloud cover over the course of the day. So this seems like a good test case to me, just based on my experience of looking at this kind of data before. So why don't we have a look at predicting or simulating what these module temperatures are going to be based on other measurements in the system. And like I mentioned at the beginning, PVLib has many alternative models for each modeling task. Today, we're going to be starting with one called the Feynman model or the Feynman model. And first, let's take a look at what this model needs. I'm using the question mark feature here. This is an IPython thing where it'll show you the documentation for the function if you use it like this. This is supported in a lot of IDEs. Otherwise, you can just view the function documentation online, and it's the exact same content as what we're looking at here. So as you can see, it takes a few different inputs. POA global, this is plane of array irradiance. It also takes temp air, which is PVLib's name for ambient air temperature, as well as wind speed. And finally, two thermal parameters that define how the module sort of thermally responds to these meteorological inputs. We can see that the parameters are described in the text here for just for reference. There's also the original papers that are relevant to this module down listed at the bottom. But anyways, I'm going to skip over all of that. So we need three inputs: the irradiance, ambient temperature, and wind speed. We could manipulate these thermal parameters if we wanted to, but it does come with some default values. So we're just going to leave it at the defaults for today. Okay, so let's get our three weather inputs. One of them is the ambient temperature we already saw. Here I'm pulling out the wind speed measurement from the system. And finally, if we go to the irradiance data frame, here's just one of the plane of array irradiance measurements. And all we have to do is pass those three inputs into the function that we were just looking at, the Feynman model. And now we have an estimate of module temperature. And this has been just simulated from these other three inputs. So it's pretty darn easy to do. The next, the obvious question is, how good of a job did our model do? So now we're going to generate a similar type of plot that we were just looking at above, but this time it's going to overlay our modeled module temperature using the Feynman model. And here's what that looks like. So everything here is the same, except for now we have a new black line, which is our modeled module temperature. And generally it looks fairly good. At least it's following the right trends. It increases with the measurements, it decreases with them more or less. But it's not perfect. Certainly it seems more jagged, more spiky than the measurements. It also seems to be sort of anticipating what the measurements are going to do in these variable conditions. For example, it rises in this upswing sooner than the measurements do. And similarly, it falls before the measurements do. And this is a well-known phenomenon. This is due to the Feynman model being what's called a steady state temperature model. And what that means is that inherently it assumes that the weather conditions are changing fairly slowly enough to assume that they aren't changing at all, basically. And on a variable data like today, those assumptions are violated to a pretty large extent. And as a result, you get these unrealistic outputs. Okay, so what can we do to improve this? Well, one thing we can do is consider thermal transients. And so there's a few different ways that we could do this. There are some temperature models that have thermal transients built into them. PVLib does provide some of those. Here, what we're going to do is to add thermal transients sort of after the fact. And so we're going to start with our Feynman model predictions and then modify them to include the effect of thermal transients. And for that, we can use this Perelman model developed by Matt, who you just heard from before. All we have to do is give it the module temperature we just calculated, as well as a couple of other inputs. Again, the wind speed, and then this unit mass parameter. This effectively defines the thermal inertia of the PV module. And this is pretty easily calculated from just datasheet parameters. So you can check the function documentation for how to exactly perform that calculation. So I'm going to run it. And now I have a new variable, tmod Feynman, and now it is modified with Perelman. So let's see how it looks now. This is, again, the same plot again. Measured ambient temperature, measured module temperature, but now black is our model, including the effect of thermal transients. And we can see that it's has improved significantly since last time. The jaggedness is now in line with what we see in the measurements. It's tracking it fairly closely, and in many parts of the day, the model is closer to the mean of the measurements than any of the individual measurements are. At least in some parts of the day, it looks like that. So this is a pretty satisfactory result, if you ask me anyways. At least qualitatively, just for this one day. But as I mentioned, this is just one model from the perspective of our system modeler. Maybe they want to evaluate all of the options in PVLib. We're not going to do that today, but we're going to evaluate some of them. And so just like PVLib has a pvlib.temperature.feynman function, it has one for the PVsyst cell temperature model. Here I'm being a little bit fast and loose with the difference between cell and module temperature, but it's good enough just for this example. There's another function for the Sandia Array Performance, SAPM, cell temperature model. So why don't we go ahead and run both of those, and you can see that their use is quite similar to what we did with the Feynman model. You, again, just give it irradiance, ambient temperature, and wind speed. The SAPM model needs a little bit more with these specific parameters that define what type of PV module it is and how it's racked. But anyways, both of these are quite simple to use, even so. And so now we have 4 different estimates of module temperature, if you can keep in count. We have our original Feynman model, we have the Feynman model modified to include thermal transients, and then we have these 2 new ones that we just calculated via the SAPM and PVsyst. And what I'm going to do is bundle all of these into a single data frame, a single variable, just to keep it easy and have all of my models in one place. And now let's get a little bit more serious about performing this validation. And what I mean by that is, instead of just making plots and visually saying, yeah, this looks pretty good, or no, this isn't lining up very well, now we're going to quantify, actually quantify some error statistics here. So recall that we have 4 different measurements of backup module temperature. One thing we can do is just take the median of those 3 measurements on a timestamp by timestamp basis. And that will hopefully give us the best estimate of what the actual module temperature is in reality. In practice, you might want to do some exclude one of the measurements because maybe you don't trust it, maybe it's got data quality issues. And that's what I've done here. That's why there's only 3 instead of 4. Maybe you would want to perform more careful filtering. In any case, I'm just going to be brazen and go ahead with just taking the median as is. I'm also going to do it for an entire calendar year rather than just a single day like we were looking at before. So just, again, arbitrarily choosing the year of 2018. One filter I am going to include as an example is to only consider daytime periods. And the way that I'm calculating that is with measurements where or timestamps rather, where the measured irradiance is greater than 0. And so what this is going to do is exclude nighttime, which probably we don't really care about the accuracy of our temperature models at night because your system's not producing anything anyways. So that seems like a reasonable filter. An alternative to using the measured irradiance to calculate such a filter is to use PVLib to calculate solar position for all of these timestamps and filter down to daytime that way. And I'll give an example of that later, but for now, let's just keep it simple. And this cell is quite a lot of code, at least at first glance. I'm not going to go through all of this, but if you go and look at this after the webinar, you'll see it's actually fairly simple. Here's where we calculate some statistics, error statistics. So here's the RMSE calculation. Here's how we calculate an R squared. Here's the mean bias error. And then we make a cool plot. And why don't we go ahead and run this and see what pops out. So what this cell just did was, for each of our 4 models, it did a comparison of that model with the measured module temperature for this entire year, again, considering our basic filtering. And each of these is a density scatter plot where the modeled temperatures are on the y-axis and the observed or measured temperatures are on the x. And each model gets its own figure here, and the error statistics are shown up in the corners. And so you can see that the first three of these models, Feynman, the SAPM, and PVSYST, all look more or less the same. Maybe their errors vary a little bit, but there's not an enormous difference between any of these. And it so happens that these three models are all steady state models, like I was talking about earlier. But notice that the Feynman with transients added is noticeably a much tighter distribution in the visualization. And also notice that its error statistics are meaningfully reduced from the other models. So instead of 4 or 4.5, or maybe approaching 5 degrees Celsius for RMSE, here we're down at roughly 3.5. The mean bias error also happens to be closer to 0, although that might just be a fluke in this case. But in any case, we can see that one model is meaningfully much more accurate than the others, at least for this particular data set. Okay, so what have we achieved here? We've used PVLib to simulate and reproduce one measured quantity in a system's measured data set from other quantities in that same data set. And this has a whole lot of uses. For one, you can sort of train your models in a sense on a measured data set and then use it to predict future values. You could use it for gap filling purposes. For example, if one of your back of module temperature data becomes corrupted for whatever reason, you could produce an estimate of it using PVLib. You can use PVLib as a check to detect when you might have problems. For example, if your back of module temperature sensor detaches and falls off the back of the module, and now it's not measuring the module temperature anymore. This is a common thing that happens in reality, in case you think I'm just making that up. Having PVLib's predictions as a check on that would make it pretty obvious when that's happened. We have also compared these several models together to see which one performed best on this data set, as well as made a cool plot that maybe you can bring this to your boss and impress them and get a raise. All right, let's move on to the second use case here. This one is a little bit the reverse situation, where rather than being primarily a modeler and then bringing the data in to help me do that job, now we're switching gears and viewing this from the perspective of somebody who is more interested in the data and then bringing the models in to help them with that. And so the use case here is that of an O&M analyst or maybe an asset management analyst. But anyway, somebody who is interested in analyzing, for example, the most recent month of a given system's performance data. They're looking through the data, trying to calculate performance metrics, or maybe they're performing a capacity test, something like that. And they see some things in the data that they don't quite understand. And what PVLib can do in this case is can model the system and provide context to what they're seeing in the data. Okay, and I'll explain more about that in just a minute here. So I know quite a lot about this use case because I used to do it all the time back in the day before I joined the national labs. The place I always started when I was looking at measured performance data was the so-called power versus POA plot. And this is a plot of some components production, oftentimes an inverter, sometimes an entire system. But anyways, system production on the y-axis against plane of array irradiance on the x-axis. And this can tell you a lot about how your system is performing. Ideally, there would be a pretty linear relationship between power and plane of array irradiance. In this specific case, I'm plotting 1 month of data here. There's some pretty stark non-linearities going on, deviations from the nice linear, the primary trend. And so there's three things that I want to highlight. There's a cloud of points below the main trend here, where at sort of middle to higher irradiance, the system doesn't seem to be performing as much as it does in other times. So this is a seeming underperformance, is what this is telling me. There's a cluster of points here at quite low irradiance where somehow the inverter is producing much more power than you would expect for the given irradiance observations. That seems non-physical. There's also a cluster of points down here at the bottom where at many irradiance levels, the inverter is just producing nothing. So probably this last one is due to, it's either a data quality issue or it's a real inverter outage. And that's not quite so interesting. These other ones seem like it's not necessarily obvious what is causing these. And so this is what we're going to use PVLib to help understand what the origin of these two clouds of points is, and how we can basically what we can do about it. Okay, so this is a plot of just power versus irradiance. There's no time component here. I often find that when you see something strange in a plot of two quantities against each other, you can learn a lot by switching over to time-based plots of those same quantities. So let's go ahead and do that. Here we're plotting the same things, that same inverter power and plane of array irradiance, but just a single day this time rather than the full month. And we can see that they're both, doing the tracker thing of having a pretty broad profile. This is a particular, this day is in the winter, and so you get this double hump effect of due to angles of incidence and all that. And things seem pretty reasonable to be in the middle of the day. But I want to draw your attention to the shoulders. So this region here and this region here. This is a kind of a symmetrical morning and evening effect, where for part of it, the plane of array irradiance is much higher than the power. And for part of it, the reverse is true. The power is much higher than the irradiance. And I think that corresponds to the two clouds we were seeing in the scatter plot, where this time the power is dropping when faster than the irradiance says it ought to be. And so it seems like the system is underperforming in those times. And here's the times where it seems like the system is performing amazingly well. Hard to understand how it could be performing so well because the irradiance is so low, but we still have, medium to low to medium power production going on. And you get more or less the same thing in the afternoon with maybe a little bit of unexplained spike going on. So based on this plot, just using, let's say, engineering intuition, you can notice a few things. The fact that it's symmetrical seems pretty relevant. The fact that power stays high, or at least it doesn't drop off so dramatically like the irradiance does, means that this isn't a cloud event, because that would affect both power and irradiance, presumably, and it wouldn't affect it so symmetrically. And the fact that the irradiance drops off so sharply, basically instantaneously at the resolution of this data set, suggests that this is some kind of shading issue, where for much of the day, the pyranometer has a clear view of the sun, but then at a certain point, a shadow crosses onto the pyranometer and blocks the sun from its point of view. But this is just a hypothesis. This is a speculation on my part at this point. How can we go about proving this and becoming confident that this is what's actually happening? Well, we know that this is a tracking system. We know that it has cadmium telluride modules. From that, I would make a pretty good guess that the system doesn't backtrack, which means that it doesn't perform row-to-row shadow avoidance in the early morning and afternoon. We could confirm this by going and looking at the measured tracker angles. In fact, I have done that, and I can confirm that it's not backtracking. I didn't do it in this notebook for the sake of time. But anyways, we know that it's not backtracking, and so we know that there's going to be some amount of row-to-row shading in the array. So maybe this has, maybe the supposed shadow hitting the pyranometer has something to do with that row-to-row shading. Let's see if we can help answer that question. So what I'm going to do is I'm going to use PVLib to model what the row-to-row shading effect is as a time series for these same timestamps. And so the first step here is to calculate solar position. PVLib has a really convenient get solar position function where you give it a list of timestamps and the coordinates of the system you're interested in. And it gives you back a data frame, in this case, with solar position angles. And we're going to use those solar positions to calculate tracker rotations. That's what the single axis function does. So you give it a solar position, and a little bit of system geometry and tracking configuration, and it gives you back tracker time series angles. We could use the measured tracker angles from this system rather than modeling ones from scratch. In that case, you would have to make sure that the tracker rotations are reliable, they're not messed up somehow. In this case, it's a little bit cleaner to just model them de novo, but either way works. Okay, now that we have solar position as well as the tracker positions, we can calculate a shadow geometry due to row-to-row shading. So before this webinar, I estimated the ground coverage ratio for this system. This was just based on satellite imagery and the module datasheet information. That's a pretty useful trick to have up your sleeve, is figuring out system parameters based on sort of public information like satellite imagery or Google Street View, that kind of thing. So with a ground coverage ratio, that's all we need to calculate shaded fraction. So we have a function for that. You give it solar positions, the tracker orientations that we just calculated, as well as the ground coverage ratio. And now we have an estimate of the shaded fraction. Okay. By the way, what I mean when I say shaded fraction, if you imagine as the sun approaches the horizon, you have if your modules are rotated quite steeply, then you'll have a shadow sort of start to creep up from the bottom, up the entire height of the row. That fractional height as the shadow creeps up is what I'm talking about with shaded fraction. So it's a fraction of the overall tracker bandwidth, tracker collector width is what I'm referring to here. Okay, so now that we've calculated that, why don't we see if we can notice anything useful about how plane of array irradiance changes based on our modeled shaded fraction from PVLib. And this is what it looks like. So on the extreme edges of the day, shaded fraction is quite high. And then as the sun rises higher and higher, shaded fraction eventually goes down to 0. And for most of the day, the system has no shading whatsoever. But one thing we notice, one thing that's readily apparent, is that the drop off in the irradiance occurs right at about where shaded fraction is 0.5. And that's true in the morning, also seems to be more or less true in the afternoon. And that seems like probably not a coincidence. Why don't we go ahead and try to verify that more quantitatively rather than just eyeballing it. So here I'm calculating a couple of data filters, one indicating where the shaded fraction is less than 0.5, one where it's greater than 0.5. And we can use that to modify the plot and label points accordingly. So this is the same plot we were just looking at, but now green points indicate when shaded fraction is less than 0.5, red indicates where it's greater than 0.5. And we see that this is quite it lines up exactly well, basically, down to just the resolution of the data set. So from this, I mean, why would sensor shading occur when shaded fraction is specifically 0.5? Well, it so happens that in many tracking systems, what they do is they mount the pyranometer on the torque tube of the system. And since these trackers are symmetrical, that means the torque tube is in the middle of the table width. And so as soon as that shadow crosses halfway up the width of each table, that's when it is also going to start shading the torque tube and anything mounted on the torque tube, including the pyranometer. So just based on this plot, what we figured out is not only what's going on with why this pyranometer is reporting strange data, we've also discovered exactly where it is, how it's mounted, which is pretty amazing that we can do this just using measurements and a little bit of help from PVLib. Anyways, so now that we know what's going on, why don't we use this knowledge to do some more data labeling? And so what we're going to do is go back to the scatter plot that started this whole exercise, the power versus plane of array irradiance, and label each of those points, color it essentially, according to the shading condition that PVLib is telling us. So we're going to label 3 different shading conditions. One where the shaded fraction is 0, that is to say no shade. one where there's some shade, any amount of shade, and one where specifically more than half is shaded. And again, that corresponds to when we expect the pyranometer to be experiencing shading. Otherwise, this is the same scatter plot. And we can see that these shading conditions essentially perfectly label the different clouds that we were talking about earlier. So with sensor shading, that explains this lower plot or lower cloud where instead of, by the way, now we can reinterpret this, instead of AC power being high for the irradiance, in fact, the irradiance is just too low and the AC power was normal. We can also understand this cloud of points here where the irradiance measurement is reliable because the sensor is not shaded, but the array does have some shading on it. And so as a result, you get a reduction in performance. Okay, so this is all a pretty consistent story and also a good demonstration of how you can use models to help label data, even though at no point in this process did I actually feed the data into PVLib. It just did a whole bunch of hypothetical calculations and it lines up, basically perfectly. One other thing I want to demonstrate here is, okay, now that we understand the data, again, putting ourselves in the mindset of a performance analyst, maybe I want to perform a capacity test, maybe I want to calculate a performance ratio. In any case, I don't want these poor performing points polluting my analysis or biasing it, because it doesn't really represent the ideal system performance because there's all this shading. I definitely want to exclude these points because the irradiance measurement is unreliable. And so what we're going to do is, besides just labeling these points on a graph, we can use our modeled shaded fractions from PVLib to calculate data filters so that we can exclude those values altogether from whatever analysis we do next. And in fact, we already have that filter available from the cell above. And so now we've narrowed down our data set just to times where there is no shade anywhere. And now we're left with just this nice linear trend, a few outlier points that you might want to exclude also, as well as that remaining inverter outage that we haven't done anything with yet. So just for completeness, again, to make a nice plot to show your boss or impress your friends or have your parents put it on their fridge or something. Here's a plot that tells the whole story that we just did, starting with all of the measurements, labeling each point according to our shading model from PVLib, and then finally filtering down to just the unshaded times. So just to take a step back and reiterate what just happened, we used PVLib not to analyze the data per se, but to sort of be an analyst's assistant in a sense, where based on my intuition and my data exploration, I thought, maybe it's this one thing, and I can use PVLib to help me calculate what that one thing would be, and then bring that into the data and perform the comparisons myself. So as a sort of assistive tool, PVLib can be quite helpful. And for a modeling tool, I think a lot of people don't really understand how useful a modeling tool can be in more O&M oriented contexts. Hopefully this was a good demonstration of that. Just to mention some other things to spark your interest in case you want to continue on with this data set in PVLib yourself. To get a truly clean data set, you might want to remove these outliers. You might want to remove this inverter outage. Some things you could do there are, for example, use modeled solar position from PVLib, like we did earlier, to filter the data set down to only include daytime periods. And that might help us identify times when, if the sun is above the horizon and the inverter is producing 0 or maybe some very small amount of power, that might reflect an inverter outage. You could try to estimate the production loss associated with that inverter outage by just making a system model and estimating what the production would have been had the inverter been online during that outage period. You could also explore things like, does this sensor shading happen every day of the year? Maybe it only happens at certain times of the year because of just the system geometry. That's a fairly common effect for sensor shading is that it only happens in certain parts of the year. And so you could use, for example, the modeled solar azimuth angles that we already have to understand when and how this particular sensor experiences shading. So that's about it for this notebook. One other thing I want to highlight before moving on is if we scroll way back up to the top, there's a few helpful links up here. For one, there's PVLib's documentation. The main thing I want to highlight is within PVLib's documentation, we added a conventional system model example of using PVLib to do a complete end-to-end performance model, like what Matt was talking about earlier, of you start with NSRDB data and you get AC power out of it. So I'm not going to go through this today, but I just want to make you guys aware that it exists and show you a cool plot at the end for, here are the two, this is daily production on the y-axis here and a full year on the x-axis. Look at how well the inverter measurements match up with our model, pretty good. The other thing I want to mention is that PVLib Python, I just want to emphasize this, it's open source. That doesn't just mean that you have access to the source code. It means that it is developed by users. And in fact, I was a contributor to PVLib before I really got, I mean, I was a very casual user of PVLib when I first started contributing to it. And then I found out that, boy, I really like this project and I want to get more involved. And here I am today. But PVLib's code base is the product of over 100 people at this point. Many of those people are not professional programmers. They might inaccurately consider themselves to be poor performance modelers or otherwise not qualified to contribute to a project like PVLib Python. I encourage you to not give into imposter syndrome and if the idea of contributing and supporting a project like PVLib Python appeals to you, I very much encourage you to reach out and see how you can get involved. This is very much a community-oriented project, and it gets better when people make it better. So anyways, I'll get off my soapbox here. I think that wraps it up for our tutorials. And now I think we're going to open it up for any Q&A that hasn't already been addressed.
I don't think we've been able to answer the majority of questions, but we do have a couple here. I'm not sure if you're able to access both use cases. But if you'd like to look into Q&A, Mark has two good questions. One for case one, where the temperature graphs. So the temperature graphs all for stock temperature model parameters, or were they tuned? That's our first case one question.
Those are all using the default model parameters. So of course it would be easy to tune the models to tune those thermal parameters to better fit the measurements. In this case, I didn't do that. I just used the defaults.
Thank you for that. And then for case two, Mark says, very nice demo, by the way. Thank you, Mark. Do you think that the fork and the scatter plot at higher radiant show some sort of AM/PM effect?
Yeah, I noticed that too, and I didn't get into it. I suspect it probably is. Temperature is the first thing that comes to mind because that's a difference in AM and PM, and also something that isn't directly accounted for in that plot. It could be that there's some other effect going on. I didn't investigate it, but yeah, I think you're probably right that that's a morning afternoon difference.
That's a great clarification. Thank you. Another question here. Do you recommend to use POA irradiance or GHI?
It a little bit depends on the case. In general, it's a reasonable starting point to use POA irradiance for any kind of modeling or analysis tasks because all else equal, there will be less error in whatever you're doing. And the error I'm referring to is if you start with GHI, then you have to estimate a plane of array irradiance based on those GHI measurements. And those estimates require models, and those models are not perfect. And so by starting with GHI and going to POA from there, you're introducing that model uncertainty. Whereas if you start with measured plane of array irradiance, then you get to avoid that additional uncertainty. But that said, there's all kinds of reasons why you might prefer to use GHI in any given case. Maybe your GHI sensor is not subjected to row-to-row shading, for example, and so it's more reliable in certain times of day. Maybe the data logger lost some of the measurements from your POA irradiance, and so you supplement it with the system's GHI. So yeah, there's a lot of reasons to prefer POA, but it's not a hard and fast rule.
The next question here says, for hourly simulations, what are the advantages of using PVLib over PVSYST in terms of accuracy?
They're fundamental. They're quite different tools, PVLib and PVSYST. PVSYST, I mean, well, one advantage or disadvantage, depending on how you look at it. PVSYST has a nice user interface. Well, it has a user interface. PVLib, of course, is only used from code, so that's a big difference from the start. But for in terms of accuracy, it depends. I don't think it's very productive to think about particular software as being more or less accurate than others. Really, it's about the models that the software uses and the modeling choices that the analyst makes, or that the person using the software makes. And so, I mean, PVSYST is certainly a great tool. PVSYST in the hands of somebody that doesn't know how to use PVSYST well, me, for example, I'm not a PVSYST user. And if you wanted me to finance a system using PVSYST, I would do a terrible job. I would do a much better job with PVLib because I'm a better user with that tool. And I'm sure that, you know, that the reverse is true for many other people, that PVSYST is what they're comfortable with, what they know how to use and get an accurate model out of. So in general, I think you can certainly get very accurate models out of both of these tools, but my answer would be that it's more about the user than the tool.
Thank you. The next question here was, does anyone know of the starter examples for performance modeling with PVLib Python, but then analyzing the economics with PySAM?
I'll chime in first on this one. I don't know any at the top of my head that publicly available. It's definitely something we've talked about, something we wanted to add to the list. Maybe there's been tutorials where people have used both. I know, I'm pretty sure I've seen instances where people have used both. I'm just not sure if there's a place I can point you to yet. Kevin, you know of any?
No,
It's definitely on the list of stuff to do.
Yeah, and it's certainly possible. I don't think it requires any changes in our tools to make it happen. It's just a matter of writing up a nice, clean example and putting it online somewhere useful.
Great, thanks for jumping in on that. It looks like that is the end of our list of questions. We might leave it open for another minute or two to see if anyone else has a question, but otherwise, we're good on this end.
I'd like to just say something real quick. Mark, your comments are very appreciated. I just want to make it explicit that this level of I don't know, introspection, that's not the right word, but level of, you know, detailed thought, depth of thought about how PVLib can be better, and, you know, not just surface level comments. I think that's great. It's exactly what PVLib and really any open source project needs from its community. So I just want to say thanks for bringing up those points, especially about the usability aspect. I agree that I agree with the sentiment behind them. I don't have a great answer for how to make it better at this point in time, but I just wanted to say thanks for bringing that up, and please continue to do that kind of thing.
Oh, looks like we had one more come in from Joe and a final comment from Mark. But Joe's question, Kevin, can you repeat the estimated GCR for the one example, the module data sheet?
Yeah, so I can take a couple minutes as long as there's no other questions here. I can just do a quick demo of it live. So GCR is the product of two, not the product, it's the result of two quantities. The first is the row-to-row spacing, often called the pitch. And from that, you can estimate it from satellite imagery. I can't do it in Google Maps. I wish I'd pulled up Google Earth. But anyways, in Google Earth, you can use the ruler tool to measure the distance between 2 points. What I often do is measure not just one row to the next, but go across, 10 or something, and then divide to get a single row spacing so that my error is reduced. But anyways, that gives you one of the two necessary parameters to calculate GCR. For the other one, you got to know how wide your tracker tables are. And the best way to do that typically is if you know what modules are installed and you know how many of them are next to each other on the tracker, and you know what orientation they are, portrait or landscape, then it's a little bit of arithmetic to calculate it. In this case, you can't see the module orientation or the number of modules per, across the width from the satellite imagery. In that case, you can from Google Street View for this system. So there, if you went and looked at it, I think you would find, if I remember correctly, it's 4 modules high and they're all in landscape orientation. And then if you go in the data sheet for these modules, they're for Solar Series 4, I think, you get the relevant dimension multiplied by 4. And then I think I added, a centimeter or something gap between the modules. And then take the ratio and that's your GCR.
Great, thank you so much for that, Kevin. It looks like we didn't have any additional questions come in, so if you're done, no question, just a comment that the series of tutorials was outstanding, and thank you.
Thanks for coming.
All right, and then just as a reminder, these recordings will be available on HeroWebs next week. Part 1 and Part 2 are available now. And then we will also be posting any of the additional resources, such as the links from today's demos. Those will all be part of those recordings. Thank you all so much.
Yeah, thanks again, everybody, for coming and for your attention.
Thank you.